Okay, so we're going to look at one more example in this section, a generalized example, so that we can establish a really important rule about finding derivatives. Okay, so if we look at this function right here, we know that that is the general form of the slope of a line, right? That's the slope-intercept form of the equation of a line. So we're really familiar with that, and we know if we look at that, we know right away the slope of that line is m, right? And what we're going to do right now is find the derivative of this function here at some particular x value a. We don't know what value x value it is, so what we're actually going to do is find the derivative in general for every value of a that x could be. In other words, the derivative at all points for this equation. But intuitively, we already know that because the derivative represents what aspect of a line geometrically? Right, so the derivative is the slope of the line. And if we know the slope of this line is m, what should we anticipate the derivative will be equal to? Let's see if that is the case. So we know from our general definition of the derivative that f prime at any particular value of a is equal to the limit as h approaches 0 of f at a plus h minus f at a all over h. So let's see what happens when we substitute a plus h and a into this function here. We'll call this f of x. Y and f of x, same thing. Well, when we substitute in, we'd see f at a plus h is m times a plus h, just plugging in for x, plus b, it's the top left part, minus f at a would be m times a plus b. And that's all divided by h still. And now again, we're just doing some basic algebra here. So let's simplify that numerator a little bit. This is an h, not an x. Oh, did it again. Good grief. Okay, so when I distribute here, I would have ma plus mh plus b minus ma minus b. And now let's see what happens here. I can see right away I have some like terms here. ma and minus ma cancel. B and minus b cancel. And now we're real close. We're real close. Things happen real quick in this example. Because everything almost drops out in the numerator, so we're left with just mh over h. But we can see real easily, why does that keep happening, that h cancels. And now we're left with the limit as h approaches 0 of m. M is just a constant value. So as h goes towards 0, m is going to keep being m, and our limit would be m, which is just what we expected, because we know that the slope of any line in slope-intercept form is given by this value m. So the derivative at a particular value a, any particular value of a, would be equal to m. Again, this is just reinforcing the derivative is equal to the slope of the tangent line. And if the function is a line itself, then the tangent line is just the line. The derivative is the slope of the tangent line. So for a linear function, the derivative is just the slope. This is a general rule that's always true about any linear function. So that's really important. Let's go ahead and generalize that. We can say if, this is an important theorem here for us, important rule that's always true, if f of x equals mx plus b is a linear function, so if we have any linear function, then f prime at a equals m for all a, for all values of a. This is a really great and important rule for us. The derivative, this is what it's telling us, the derivative of any linear function is the slope of the linear function, just that value m. So now, if I ever ask you to find the derivative of a linear function, it's super easy. You just say whatever that value of the slope is. right? Another rule that comes from that really quickly and easily. Suppose f of x equals b. So it's a linear function, but it's a more specific example. If it's just equal to some specific constant, right, we call that a constant function. So if we have f of x is a constant function, then what's the slope of a constant function? Right, the slope of a constant function is a horizontal line with slope 0. You can just look at it, m equals 0, which is what causes this first term to drop out. So the slope of a constant line is 0 for all values of a. Anywhere on a constant function, the slope is 0, and so the derivative is 0. Okay, so here's your first two rules of differentiation. Now, you can find the derivative of any linear function and the derivative of any constant function in an instant without having to do any computation because of these two very powerful rules. So you definitely want to make sure you tuck those into your brain space. Let's look at an example where we can apply those. Let's consider the function f of x equals 9x minus 5. And we just want to find f prime at 2 and f prime at 5. Okay? So it is as simple as you might be thinking it is. Right? When I say f prime at 2, I mean find the derivative at 2. What do you notice right away about f? F is a linear function, so f is linear. So, what is its derivative? Well, the derivative is equal to the slope. The slope is 9, so the derivative at 2 is 9. There we go. That's simple. Piece of cake. And remember, we said it's true for all a, so even if I move to a different place on the x-axis, I still have the same linear function with the same slope and the same derivative, so that would also be 9. Okay, so now we know we can find the derivative of a linear function really, really fast. It's just equal to the slope. We're going to continue to add more rules for differentiation so we can get faster and not have to do this long process up here every single time. But for the rest of today and tomorrow, this is exactly what we're going to practice. So you're about to get a worksheet where you're going to practice these examples. Work together. Make sure you're practicing using this formula so you get used to how it works and see the patterns. Make sure you use both formulas so you have a good grasp on either one, because different problems might present one formula or the other. Okay, so that's what we're going to practice today and tomorrow. Enjoy.